All right, so in this lesson we are going to study about ellipses and the equation of any ellipse. All right, so an ellipse in general is a conic section, and at the end of this lesson I can fit in a short explanation of why we call it as a conic section like that. But let's right now get into exactly what it is to be an ellipse and how we can identify the equation of an ellipse. All right, so in my graphing space right here with decimals, let me put in the graph of an ellipse, the picture of an ellipse right here. All right, so a picture like this is called an ellipse. So we can think of that as a circle that's being compressed on one side right here. So think about from a nice and round circle. Think about we compress vertically that circle to get an ellipse. Or again, think about the same nice round circle we compress horizontally to have an ellipse. And so now that was just one way of explaining it, but let's just basically look at a shape like that being called an ellipse, and let's look further into the characteristics of an ellipse. All right, so let's say with an ellipse that's currently on screen right now, it looks longer on the vertical side versus some other ellipse here that looks longer on the horizontal side right here. So in that way, as a characteristic right here, any ellipse has two important axes. And so now I put in the axes. And so any ellipse here has a set of axes, as I said earlier. The axis that goes along the longer side of our ellipse is referred to as the major axis. So in this case, right here, in our particular picture right here, the longer axis happens to be horizontal. And so now the axis that's parallel or goes along with the shorter side of our ellipse here is called the minor axis. So in this case right here, since our ellipse looks horizontal, longer on the horizontal side, the horizontal axis is the major axis, and the vertical axis here is the minor axis. And understand me clearly that when I mean axes, now I'm not particularly saying it's the x-axis or the y-axis. I'm just saying that in the way how the ellipse looks like that, horizontally or vertically like that. If it's longer horizontally, then the axis that aligns with that particular longer side is going to be called the major axis. And then the axis that aligns with the particularly shorter side is called the minor axis. So in that case, allow me to do another demonstration. As another ellipse right here, it could be longer vertically and shorter horizontally. And let me now bring in the picture a little closer. And so now with a picture like in this situation, right here, this vertical axis, and once again, not necessarily the y-axis, the vertical axis of this ellipse here in the picture is now the major axis, and this horizontal axis here of the picture is the minor axis. And then throughout all cases that I've been showing earlier, then the two axes will always cross at one particular point, and we call it it's a center. So right here in our picture right here, the center of the ellipse is right here. So any ellipse has a center, and that's where the two axes here cross each other. And now let me bring it in a closer look right here. Let's say any ellipse here has another special characteristic. Aside from the axes right here, any ellipse has a set of foci. All right, and now let me show the picture. Right now we don't need to get into any precise details yet, but let me show the picture of the set of foci here for our particular ellipse. All right, so the 2 points that just now popped out right here, they have a special relationship with the ellipse that's currently in the picture right here, and these 2 points are called the foci of our ellipse. And currently in this picture here, the major axis is the vertical axis, and again, not necessarily the y-axis. currently my foci right here are right on the vertical axis here. Let me now change to a different picture right here of another ellipse. All right, so now in this other picture right here, the ellipse is longer horizontally. And so the foci in this case right here are located right on the longer axis right here, which is the horizontal axis. And so now you can see as a generality right here, the set of foci are always found on the major axis. Okay, but so those are some of the basic characteristics of any ellipse right here. And now we're gonna really get precise into how all of that, any of those characteristics will be characterized by equations and values of the equations again. Okay. All right, so let's look at the following equation: x squared. This equation I just now wrote down on the board right here, x squared over 16 plus y squared over 9 right here equals 1. Let's write down another equation. This equation now that I just wrote down right here, x squared over 9 plus y squared over 25 equals 1. Now, before I get into the computer screen and showing the picture right here, let's have a close look at the two equations right here to recognize some common characteristics. So the two equations here has the perfect square of x and the perfect square of y, and they both equals 1 on the other side, on the opposite side of these equations. Now these numbers right here, let's look at them a little further. I purposely use some easy to recognize number. But as far as something to observe, something to note right here, the 16 here really is a 4 square. The 9 here is easily recognized as a 3 square. Okay? And this equation down here, the 9 in the denominator right underneath, that x squared is understood as a 3 square. And that 25 here right underneath, the y squared is understood as a 5 square. Okay? So another way of writing it, this top equation here, okay, so the top equation, another way of writing it can be rewritten as x squared over 4 square plus y squared over 3 square, all equals 1. This other equation here similarly can be written as, all right, so that other equation right here can be similarly written as x squared over 3 square plus y squared over 5 square. So the common characteristic among these two equations right here is that it has the x squared term over some coefficient square. It has some square term on the y over some coefficient, some value, some constant square. Okay, so generally speaking, any ellipse has the following equation. And that's what I generally recognize about any of those equations that I've written on the other board. Okay, so now ladies and gentlemen, an equation of this form right here, now further as an intention, the a and the b right here, even before the square, are required to be positive value. So now before getting into this equation, allow me to put in another slide, a small introduction. Okay, so in any of these equations that's in this form right here, let's say a and b are positive real numbers, and that's how I'm writing it. Let a and b be positive and real numbers. So now this equation here, okay, this equation here is an equation of an ellipse. But then, as I was saying earlier, any ellipse has some characteristics. So this equation here is the equation of an ellipse. And let's now list down the characteristics of the ellipse that's described by this equation right here. Now the way I'm seeing it, this equation here is the equation of an ellipse with the characteristics that we're about to explore right here. Okay? All right, so now in my graphing space, allow me to put in the grids of our graphing space right here. And so let's say with this equation right here, let's now use some graphing device to quickly see the graph, and then we're gonna pull out the characteristics of something like this. But so now with this equation here, according to the definition we've had earlier, then A equals 4. So we always want to write it in the form of some value square, some positive A value square, and some positive B value square. And A is the value specifically the being in the denominator of the x squared term, and the B is the value specifically B4 square being in the denominator of the y squared term. Okay, in this general equation right here. Okay, and so now let's put it on screen right here. And I can see that B here in our equation is 3 for this specific equation. And it's always going to be 1. All right. The equation on the board just now has the ellipse as pictured in this graph right here. Okay. This equation, x squared over 4 squared plus y squared over 3 squared equals 1. Okay, but now let's look even further into that picture right here. So in the way how it looks right now, this ellipse has the longer side aligns with the horizontal axis, and the shorter side aligns with the vertical axis right here. Now we can put the axes on, and so now in this picture right here, the way how I'm seeing it, this ellipse is centered at the origin 0, 0, and this is also where the two axes, is the vertical axis and the horizontal axis, cross each other at the center of 0, 0. Now the axis itself right here aligns perfectly with the vertical and the horizontal x, y, and x axes. And so in this case right here, and in this particular picture right here, since the longer side of our ellipse aligns with the horizontal axis right here, then the horizontal axis of the picture here of the ellipse here is the major axis, and the shorter axis appears to be the vertical one. So the vertical axis here in our picture here is the minor axis. But now specifically for this particular equation here, then the major axis appears to be the x-axis, and the vertical minor axis appears to be the y-axis. And further, let's now look at another characteristic that was not mentioned when I was giving the brief introduction. But now, since we have the axis is on right here, our particular ellipse here intersects with the axes here at these intercepts right here. Now, on the major axis, our ellipse here crosses the major axis at -4, 0 and 4, 0, which is also just simply the x values -4 and x value +4. Similarly, the same ellipse right here crosses the y-axis, which is now in our case right here the minor axis. The intercept here is at 0, 3 and 0, -3, or we can just simply think of that as y equals 3 and y equals -3, but that's on the y-axis. And once again, our ellipse here is centered at the origin, where the two axes here align with the x and the y-axis. And now further, I'm going to put in the set of foci for this particular ellipse right here. And so just like how I was giving that brief introduction, then the set of foci will always be found right on the major axis right here. So this is where we can find the set of foci. And we will get precisely into how we can calculate these values right here. But so now, since our major axis is right on the x-axis, so these foci right here has y coordinate 0, and the x coordinates come out being some negative and some positive, some two symmetric values here. So that's what we recognize as far as the characteristic of this particular ellipse generated by the equation I wrote down on the board. And now one more time, let's look at another equation, but quite similar with the earlier one we pulled on the graph right here. So x squared over 3 squared plus y squared over 5 squared right here. All right. And so now I can see that this coefficient 3 squared right here, our value a is 3. This coefficient 5 squared right underneath that y square, our b value is recognized as 5. Okay, let's now once again swing back to the computer screen and have a look at that picture of the ellipse generated by this equation. All right, and now for this second equation right here, it gives the following ellipse. All right, and so now observing this ellipse right here, I note that the ellipse in this picture over here is longer on the vertical side and shorter on the horizontal side right here. Or another way of saying it's longer vertically and shorter horizontally. And so in this case right here, now we're putting in the axes. You can see that the major axis must be the vertical axis, and the minor axis is the horizontal axis. And specifically for this equation that I've just now written on the board right here, then the set of axes is once again aligned perfectly with the x and y axis of our graphing space right here. And this ellipse also has a center at 0, similar to the earlier ellipse. And again, similar characteristics. This ellipse has those intercepts found at 0, -5 and 0, 5. On the vertical axis, we have -3, 0 and 3, 0 on the horizontal axis right here. So once again, it got 4 intercepts, and let's now put in the foci. And so just as expected right here, the foci should be found right on the major axis right here. So in our case right here specifically, we're looking at 0, 4 and 0, -4, because the major axis now is the y axis in this case right here. And again, we will get particularly precise about how we can find these the value 4 and -4 right here, and provided that in this case right here, since the foci are found on the y-axis, that's why x coordinates, of course, equals 0. All right, so drawing from the two quick little equations, and we have seen the picture right here, so let's track down some common characteristics right here. The ellipse throughout the two pictures we've seen from the two equations I've had on the other board. They both have center at 0, 0. Okay, and they have the intercept. Now, in this case right here, since they both, intersecting on the x-axis and the y-axis, or another way of saying it, that the axes is aligned perfectly with the x and y axes. So I would say the x-intercepts those were found at, on the x-axis, x equals positive or negative a right here. Okay. For example, quickly just now, x squared over 3 squared, we recognized a equals 3. On the picture right here, this is the ellipse for that equation right here. So on the x-axis or on the horizontal axis right here, 3 here and it's -3 here. And the intention is that a is the coefficient that was put in the denominator of the x squared term. Okay, and so now similarly, you can see that b being the coefficient that's in the denominator of our y squared term. Okay, and we recognize that b equals 5 in this equation. And so on the picture of the ellipse, it crosses at 5 and -5 for y. So I can see that now I have y-intercept being listed as y equals, because it's on the y-axis, plus or minus the b value. Okay, but another way of saying this needs to be more precise. So we can write this. So on the x-axis right here, I want to show the more general the understanding of that. So on the x-axis, thinking of the x-axis here as the horizontal axis, then we're looking at a, 0, and for the other one, minus a, comma 0. Those are the two intercepts right on the horizontal axis. So now I want to generally see this x-intercept here as the horizontal intercept. Similarly, the y-intercept here, right on the y-axis, we got y equals plus or minus b. But more generally, we can see this as 0, comma b, and 0, comma minus b right here, because I want viewers and learners to understand this as these are the intercepts on the vertical axes. Okay, and so since the vertical axis in our special case here is being the y-axis right here, that's why x coordinates appear to be 0, and these are just simply the y values. Okay, so these are some characteristics we have already pulled out, but there are still more characteristics. All right, and one more time, allow me to get into this board right here, look back at the two equations we've had it written down here. In the first demonstration equation right here, specifically we were in that case where a is greater than b. Okay, for this equation. And for this other equation right here, a is less than b. And of course, we are already set ourselves under that strict requirement that a and b are both positive real numbers. But now specifically in this equation here, I pointed out that case where a is greater than b. And in this other equation, I pointed that out that where a is less than b. Let's find out some further characteristics, but that depends on the two separate cases here. Okay? So now on the graphing space, when a is a coefficient that's greater than b, and corresponding to that top equation I wrote on the board, the picture once again looks as following. We have an ellipse, and for this ellipse here specifically, the major axis is the x-axis, and the minor axis is the y-axis. Let's now put in the axes. All right. And the foci, as I've mentioned earlier, are found on the major axis. So here we have the foci. Okay. And those have coordinates minus 2.646, comma 0, and positive 2.646, comma 0. We will get more detail into how we can calculate these, but it makes sense now that these foci got y coordinates 0 simply because in this picture over here, the foci are found right on the major axis, which happens to be the x-axis. All right, so my board will get lengthy, so allow me to switch to this document camera right here. But so now when we're in that special case where a is greater than b, the picture we have just investigated pointed out that the major axis of an ellipse, in this case right here, will be the x-axis. Or, as a precise equation, y equals 0. And so needless to say, the minor axis was recognized as the y-axis. And the equation for that is x equals 0. And so now, in that way, foci, as I mentioned earlier, were found on a major axis. So foci appears to be some value c, some positive value c, comma 0. The right-hand side foci on the major axis here. And there's the other focus point, minus c, comma 0. And these two point together, once again, I call them the foci. And so now, precisely speaking, this c value here as a positive value, the way to calculate that, c equals the square root of the absolute value of a squared minus b squared. So this is the formula for any one of us here to generally calculate the value for c being part of the coordinates of the foci right here. And one more time being on the graph, The idea is that the value c that I was pointing out being part of the foci coordinates, that value c indicates how far the foci goes away from the center of the ellipse. And so that distance of how far negative or positive, it's just indicating to the left-hand side or the right-hand side or the left-hand side. But more precisely, it's how far we put the foci away from the center, where the two axes is crossed. And so for that reason right here, on the major axis, this value c right here is the distance from the center out to each one of the foci. And these are how we put the foci in coordinates. And now back on this board right here, let's investigate the other case where we have another equation, very similar format right here, but this time a, the coefficient that we put in the denominator of the x squared term, is less than b right here, and b is once again the coefficient that we put in the denominator of the y squared term right there. So now let's specifically looking into that case where a is less than b. All right, so in our graphing space here, this is the ellipse for that second equation I put on the board earlier. And now so in this case right here, we can see that the major axis turns out to be the y-axis, whereas the minor axis turns out to be the x-axis. And let me put the axes in. And then so now let's put in the foci, the set of foci. So again, generally foci are found on the major axis, and that's why we have these points right here. And once again, being on the y-axis specifically, x value or 0, but y value here now generally indicates how far the foci are put away from the center of the origin. And so this is the value c right here. We got c right here and negative c. Okay, and so in that case, now let's generalize that. All right, so when a is less than b, the major axis is the y-axis, where precisely we call that the line x equals 0 as an equation. The minor axis turns out to be the x-axis, where we have that equation y equals 0. And now for the foci, we're looking at 0, comma c, as we have seen in the picture. And 0, comma negative c. And once again, for c being a value calculated by square root of the absolute value of a squared minus b squared. And so now, as a final clarification, in this case right here, and in any one of the cases right here, so for that equation, c, let's apply that formula we've learned. C is always found by the square root of absolute value of a squared minus b squared. So we're looking at 4 squared minus 3 squared in absolute value. And that will give me the square root of, now 4 squared is a 16, 3 squared is a 9, 16 minus 9 in absolute value gives me 7. And square root of 7 gives that value 2.646, something like that we've seen on the computer. Similarly, for this case right here, c indicating the distance, how far we put the foci away from the center on the major axis. So square root, and now it's absolute value. We got 3 squared minus 5 squared. 3 squared is a 9, 5 squared is a 25. So we're looking at square root of the absolute value, because this difference here is a negative difference. Absolute value of negative 16, which is, after the absolute value, it's square root of 16, which is making it 4. And that's how it's consistent with the picture we've seen on the computer screen earlier. All right, so now let me bring in another equation to demonstrate the idea here. All right, so now we have some two other equations right here. Note how there are no longer just a simple x squared term and y squared term in each one of these equations. Here we're looking at x minus 2 all squared over 4. And here we're looking at y minus 1 all squared over 9. And then in this other equation here, we got x minus 3 all squared over 25 plus y minus 2 all squared over 4. So something still similar with the earlier equations we have seen right here. That coefficient in the denominator underneath the x term right here, underneath the perfect square relating with x, I'm seeing that here as a 2 squared. That coefficient underneath the y squared term right here, or something similar to the y squared term, I'm seeing that as a 3 squared. And so similar argument, 25 here is understood as 5 square, and the 4 here is understood as a 2 square. Okay, and so clearly it's still in some form. Generally speaking, these two equations comes in the form of generally some x minus a value h all square over some a square plus y minus some k value all square over some b square equals 1. That's the generality of any one of these two equations. Okay, and so now let's specifically swing over to the computer screen and have a look at the particular graph for any one of these two the equations here, and we're going to come up with some further generalization right here. Okay. All right, so this is now the graph of that equation written on the board earlier. This graph right here. The picture appeared to be another ellipse. Okay, and it had longer side vertically and shorter side horizontally. And so let's look further at that picture. But before I swing back to the computer screen right here, the value 2 for this equation and the value 1 in this equation in the y term and the value 2 in the x term right here, to recognize how it's properly aligned with the general form of the equation. I'm looking now at h equals 2, k equals 1. And I can call this now a equals 2, the value before square, and b equals 3, because 9 is 3 squared, so the value before square, that's b. So let's swing back to the computer screen, look at the picture a little more closely to recognize how these values, especially 2 and 1 in here, changes our picture. And then these values, a and b right here, how these values will have similar meaning with the earlier graph that we have seen. All right, so now with this picture of ours right here, it's an ellipse. And as I explained earlier, the longer side now is the vertical side. And the shorter side now is the horizontal side. Okay, and so it looks like what have just popped out on screen here is the picture of an ellipse. Center at the origin, 0, 0, and it's in dotted line because it's not really the equation. But if we're looking back at this, the two ellipses here, the ellipse with solid line and ellipse with the dotted line here seems to be like exactly the same shape and exact same orientation, except for this ellipse here has a different center. Okay. All right, the center just now popped out for this solid line ellipse right here is found at 2, 1. And comparing that with the ellipse of the exact same shape and scale and orientation, center at the origin, 0, 0 is here, then it looks like the only change that this equation does to the graph of the version x squared over a squared plus y squared over b squared equals 1. Again, the only change this equation does to that is that we're going to bring the exact ellipse that we have seen here. So A and B still has the exact same, A and B here still have the exact same meaning right there. And we have already understood how it affects the shape of the ellipse. But now x minus h and y minus k will generally bring the exact same ellipse here, recenter that to a new center being at 2, 1. So we investigated that through the picture that 2, 1 is the center of this ellipse right here. And the dotted version was supposedly x squared over 2 squared plus y squared over 3 squared equals 1. The dotted version you saw in the picture earlier is this equation, whereas now this equation here is the same exact ellipse, same scale, same orientation, major axis and all that. Okay, major axis being the vertical and horizontal axis being the minor axis right here. But now we got things recenter. Okay, so now let's reinforce our understanding. Let's now look into this other equation right here. So before I swing back to the computer screen, so now you can see that in this case right here, it looks like we have h equals 3, k equals 2, and a equals 5, and b equals 2. When on the computer screen, I will eventually compare this equation with the version just simply x squared over 5 squared plus y squared over 2 squared equals 1 right here. Okay, and let's compare the two so that we can understand how this will change, will be a modified version from that red picture, and then from there we're going to pull out some generality. Okay. All right, so on our graphing space here, the ellipse described by that second equation I wrote on the board, it's just now popped out right here. This is the ellipse. The center for this ellipse is at this point, 3, 2. So that is now making it consistent with what we have learned earlier, that 3, 2 is now being the center of our ellipse that we have seen in the picture just earlier. So we got center at 3, 2. That's the center of this equation, of the ellipse given by this equation. That was the center of the ellipse given by this equation. Okay? And then to confirm our understanding, let me put in the ellipse that came out from this equation, x squared over 5 squared plus y squared over 2 squared equals 1. And so putting the two ellipses side by side right here, the one with the dotted lines right here, and compare with the one with the solid line, then it looks like they have the exact same shape, same orientation, same scale, except for it got recentered from 0, 0 to 3, 2. And so in both cases, represented by the picture we're seeing now and the picture I brought up earlier, then it has quite a few similarities. So we can now pull out some common characteristics. And so now before I'm swinging back to the board right here, let's have a look at the graph, the ellipse generated by the first equation one more time right here. So now with that ellipse right here, let's put in the axes. Okay, so that first equation had the ellipse center at 2, 1, and now the ellipse here got, once again, vertical intercepts and horizontal intercepts. These are places where the ellipse, any ellipse, generally crosses the axes. And now for that ellipse given by that second equation on the board, we already saw the center at 0, 0, at 3, 2. And now let's put in the axes right here. And once again, this ellipse also has some intercepts where it crosses with the vertical and the horizontal axes right here. So any ellipse in general will cross the axes at 4 points. And let's observe the intercept a little more closely. All right. So now in that way, on my board here, we come to the following generalization here. So again, with A, B being any two positive real numbers, this general equation here is the equation of an ellipse with the following characteristics. So let's write down the general characteristic. The center, we've been seeing that through the two pictures right there. And the center is now clearly at the coordinates h, comma k. So that's the center of our generalized ellipse given by this general equation. So now you have seen in the earlier picture, since the center is being shifted away, so the axes now no longer align perfectly with the vertical and the horizontal axis in the graphing space anymore. So those intercepts I pointed out on the picture right here, I will now tend to call them, it's just my term, the h-intercept. Indicating the intercepts on the horizontal axis, and not necessarily who's the major and who's the minor axis yet, but h-intercept in my term here means where the ellipse here crosses the horizontal axis. So the h-intercept comes out, one intercept is at h plus a, comma k, and the other intercept on the same horizontal axis right there, the other intercept is at h minus a, comma k. All right. And then so similarly, those ellipses will cross the vertical axis here and at some what I call v-intercepts, the vertical intercept. And those vertical intercepts are precisely located at h, comma, k plus b, and h, comma, k minus b. All right. So these are the general and common characteristics between the two pictures we've seen on the board that came out from the two equations here. Okay. All right. And back to this board right here with this equation, second equation that I've just pointed out right now, then A is greater than B right here. Okay. So let's look at the graph to see precisely how it happens. All right. So in our graphing space, this is a picture of the second equation on that board I showed. The center it is at 3, 2. And now precisely when A is greater than B, let's now look at the axes. And so now since A is greater than B, the major axes appear to be now that longer side there. Okay? Because again, A is put in the denominator of the x-related perfect square term. So the longer side of the ellipse here is parallel with the x-axis. And so in that case right here, this line, this horizontal axis parallel to the x-axis is acting as the major axis. And so in that way right there, the vertical axis of our ellipse that is parallel with the y-axis is now acting as the minor axis of this particular ellipse. And then the grids right here is making it clear about where we can write down the equation of those horizontal axis, major axis, and the vertical axis being the minor axis here. And so now we can come to some further generalization, but specifically depends on the case where A is greater than B. When A is greater than B and our equation is in this form right here, the major axis will be the line that's parallel to the x-axis, and that's specifically y equals k. And so now note that k here is the value where it's y minus k. The minor axis here will be the line that's parallel to the vertical y-axis. So the equation will be x equals h. And again, with that equation where a was greater than b right here, foci, as we have investigated and been quite familiar with those now, foci are always found on the major axis. And then, so these are the coordinates right here. Right. So this line, this major axis, has the equation y equals 2 to be consistent with that generality we wrote down right here. And so on the major axis, these values 7.583 or negative 1.583, those are the coordinates, but it's indicating some value, some absolute distance where the foci are being put away from the center. So the center is at 3, 2, and these foci here, the coordinates read one way, but there's always some exact distance from where we put the foci to the center on the major axis. So in that case, foci are found by, as coordinates, c plus h, comma k, and minus c plus h, comma k. For c being the value calculated by the absolute value of a squared minus b squared. And so now let's look at this other equation right here. So this was that equation where a is less than b, okay? And then we already investigated that we had a center right here, okay? But here specifically, this equation represents where that case where a is less than b, all right? So now this is the picture of that ellipse. The center is at 2, 1, and let's now put in the axes right here. So just like how we have seen that earlier, so now since a is less than b, the vertical axis is taking the role of the major axis, and the minor axis aligns with the horizontal axis of our ellipse. And again, the center is at 2, 1. Foci are once again found on the major axis. So in this case right here, they're on that vertical axis right here. And so coordinates, x coordinates agrees with x equals 2 right here. And these coordinates, these y coordinates, comes out from some value indicating the distance from the center to that focus point, and the same distance here from the center to that lower focus point. And we will get to that precise formula when we're writing it down as a common characteristic. All right, so just now in that case where we have investigated, in that case where a is less than b right here, major axis now is that vertical axis. So we're looking at x equals h being the equation for the major axis. The minor axis is now the horizontal line right here, which has the equation y equals k. And the foci we found on the computer screen earlier, they got coordinates h, comma, some c value plus k, and h, comma, some minus c value plus k, and k came out from our y coordinates of the minor axis, or the y coordinates of the center. And the value for c is calculated as square root absolute value of a squared minus b squared. That's how we have characterized those characteristics, and most importantly, we came to that general form of the equation of an ellipse right here. Okay, so let's look at some examples here to see how we can apply our understanding into the different kinds of problems out there. Okay.